Hello, this is Mr. Dobson and this is my first video on gravitational fields. This video is on gravitational field strength, or as we like to call it, G. So first of all we need to think about what a field is. So a field is something that theoretically has a value everywhere in space. So if we imagine ourselves a room, so here's a room, simplest version, and I'm standing over here. If I wanted to, I could measure the temperature. So I measure the temperature here, use a digital thermometer or something, and I get a value of, I don't know, 23. I could measure a value here, I might get a 22. Here I might get 24. Theoretically, no matter where I was to end up taking a reading in this room, anywhere here, there will be a value for temperature. So there is a field of temperature as such in that room, and I can measure a value of it anywhere. Now, that's the simple concept of what we mean by measuring a value anywhere. So that's that. Now we need to think of how it pertains to the fields that we're going to be talking about. And the first one we're going to work on, if I get rid of this room here, bye room. The first one we're going to work on is gravitational fields. Now, every field will have a type of object that will interact with that field. And in the case of a gravitational field, we need to interact with it, we need a mass. So here is a mass. For this purpose, I'm going to say this is a very big mass, so we're going to call it capital M. So theoretically, there is a gravitational field permeating through all of space, and you can take a measurement of it everywhere. The field is affected by objects with mass inside it. So if we was to put an object that is massive, that is any object with mass, in the gravitational field, well, except everywhere in the universe it kind of has to be, it will affect the field. There will be a measurable gravitational effect at that point. Now, the bigger the mass, the greater the gravitational effect. So a very big mass will create a very large gravitational field around it, whereas a very small mass, which will denote little m, would create a very, very small gravitational field around it. Now, we do understand some simple concepts of this immediately. We know that if we were to take this small mass and we was to bring it near to the large mass, it would want to move in this direction because there is a force of attraction between these two masses due to their gravity. Now, the force is equal and opposite. The big mass pulls on the little mass pulls back on the big mass. But, of course, a small force that's going to be created between the two of them is going to be very, very large on this mass, but very, very little effect on this mass. And what tends to happen, therefore, is the small mass ends up moving, the large mass stays still. And this is very similar to the idea of planets, but is true of any large mass compared to a small mass. So what we tend to think about when we think about gravitational fields in A-level physics is field lines. And the simple way to decide a field line would be to think about what direction a test mass would move in. So we can take this little mass as our test mass, and what we mean by test mass is a mass that is smaller. So a test mass is a mass that is very, very small compared to the large mass. So its mass is very, very negligible compared to the large mass, and therefore the effect of its field is very, very tiny. So then we can ignore the effect of the field of our little mass here and only worry about the field of our large mass here, which makes things a little bit easier. Later on, in a future video, we'll talk about Newton's law of gravitation, and then we'll look at when we have two small masses near each other and what happens. But we'll take the simple scenario, little mass here, big mass here. This is so small that its mass is negligible, and therefore we are only worrying about the field of the big mass here. Now, in this situation, if I bring this little mass into the gravitational field of the big mass, we know immediately what's going to happen. It's going to fall towards it. Okay? Now, we know this. We've done this at GCSE. We know it. If you've ever seen anything fall, you know it's happening. There are a couple of minor points that we should make sure we're all aware of, but that's basically the idea. Now, if I was to draw on my picture here an arrow to show what I believe the direction this test mass would take if it was to fall, I would draw a line like this. I could put an arrow on it to show direction. Now, if I was to instead grab my test mass and put it, say, here, in that case, I would draw a line going like this. And if I was to move my test mass to, for instance, here, I would then draw a line going this way to show the direction it would move. And very quickly we start to see that all the field lines radiate towards the centre of the large mass. Okay, so for Earth, for instance, that would be the centre of Earth, but any mass, it's where the centre of that mass. All the field lines will head in that direction. It's worth noting that these field lines are what we call radial. So if we was to just draw a simple diagram and of an object like this, and some kind of object with mass, that is, here's a mass, we would draw the field lines radially, so in a circle, like you might have as a kid drawn rays of light coming out of a sun in a picture or something. We would draw, oh, that's not a very good one. Let's sort that out. That doesn't look like that is aiming at all at the centre of that mass. So we'll try that again. So, there we go. And that's more like it. Okay, so we got these what we call radial field lines. So that's where the word radiate comes from, and to go off in all directions. So these are radial field lines. Now, radial field lines are what we see around every round object. But if we think about the Earth, we know that's a round object. But if I was to be working in the classroom and I need a picture, so let's draw a picture. This is my classroom again. Okay, I am here. And obviously, being a scientist, I'm always carrying an apple with me so I can drop it at a moment's notice to prove I understand gravity. So there's my little apple. If I was to let go of my apple, then it would fall. Oh, I made it bigger. Try that again. It would fall towards the ground. Boom, like that. So if I was to draw my field line to that situation, put my apple back up there, I would draw a field line like this. Now, here's the bit that is a little bit confusing. I know the Earth is a round object, but if I was to move to the other side of my lab and I was to run the same experiment, so need a little apple, there it is, and I was to let go of this apple, and make it move down. There we go. It drops to the ground. Now, if that's the case, then I would draw the field line like this. And what we find is where we expect, where we expect our field lines for Earth to be radially moving in, so moving in at an angle to each other at all times, what we're actually seeing on the surface of the Earth, if this is the surface of the Earth, is field lines that look completely parallel to each other, which is a kind of strange. We know this is true, but we also know they should be radial. And the key answer to that is just that the distance between the lines, the field lines that I've drawn here, the distance between them, here and here and here, is very, 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 very small in comparison to the circumference of the Earth. To get a large difference in angle, you need a big difference in location. And when I say big, I mean in comparison to the circumference of the Earth. So you can see here, I've gone about an eighth of the way round of a circle. Now I get a nice 45-degree change in angle. If I was to go a quarter of the way, I get 90 degrees. So if I was to go 1 degree round, I would only get 1 degree of angle difference up here. Well, 1 degree of the Earth's surface is a significant amount, far more than we would ever know to be able to stand on one side and see the other and do some kind of experiment like that. Which is why, to us, zoomed in, there is no discernible angle change between these lines. They appear to us as a parallel, or the word we would use for this is a uniform, switch to my pen, a uniform field. Okay, so that's where we get the idea of a radial field and a uniform field. They're both true of Earth on a small scale. On the world, the bit of the world that we're living in, we have a uniform field, but the Earth as a whole will have a radial field. Okay, the last thing we want to think about is some stuff we pretty much already know, but we'll just remind ourselves from GCSE. If I was to take an object, this is my object, of a little mass m, and it's somewhere in the vicinity of this Earth, which is the big mass, we know that if I let go of it, it will accelerate towards the ground. Now this is GCSE level stuff, but we'll just make sure we get our heads around it. The acceleration, we would call acceleration due to gravity, and we call that g, and on the surface of the Earth that's 9.81 meters per second. Because it's acceleration. We also know from GCSE that the force experienced downwards is actually what we would call weight, and that force or weight is equal to mg. That's the mass times the acceleration due to gravity. We can see that therefore G is a measure of how strong gravity is on Earth. And that is the subject of this, or the last part of this video, is what does G mean? So G is defined as the strength of a gravitational field. It's the it's the force per unit mass on a small test mass placed in that field. So what do we mean by force per unit mass? Let's have a quick look at that. If we take the version of this equation, F equals mg, this equation tells you the force if you know the mass. Gravity is constant, so this isn't going to change, but this will change from object to object, and therefore we can't know this unless we know what object we're talking about. Not overly useful for a general term, but if we were to divide both sides by m, we end up with F over m is equal to G. Now, this is very interesting to us because this is F over m. Now, what that means is force per unit mass. That is the force that will be experienced on every kilogram of an object. Now it's generalised. Now this applies to everything. This applies to me, you, a car, a house, or a feather. It doesn't matter because it's telling you the force that would be felt on every kilogram of mass of that object. And then we see it's a constant value, and that constant value is the strength of gravity at the surface of Earth, which is why we say 9.81 is the value at sea level, because that's where it's calculated to. Now, for most questions that we're going to answer that involve this kind of measurement, that's perfectly fine. The value is not going to change significantly because we're not going to move significantly high enough. When we go on to further sections of the course, we'll see that when we do go significantly high, when we're talking about things that maybe, for instance, might be in orbit around the Earth, we then start need to thinking about G actually is not going to be that straightforward. It's not going to stay that number. This is only true when we're close to the surface of the Earth. It's worth mentioning, just lastly, that there are two ways of recording G. The correct way of recording G is the gravitational field strength as measured in newtons per kilogram. So G measured in newtons per kilogram. So that's one way of measuring it. It's also okay to measure it, as we've said, in meters per second. Per second, it's acceleration. And this is because of the fact that, if I can find a bit of space, we have two equations, W equals mg, which theoretically in this equation G is, if this is newtons and this is kilogram, if I took that to there, then we know that G must be in newtons per kilogram. But we also know that from Newton's second law, F is equal to ma, and we can see these are both measures of force, these are both measures of mass, which means this is basically the same equation, which means G must also be equivalent to a measure of acceleration, and therefore we can give it in the units meters per second squared. Which way round to do it? Well, when we're doing questions purely about gravitational concepts, we'll tend to use this value. When we're doing questions where we're talking about objects moving or falling and they've got velocities and speeds, then we're more likely to use this because it will probably be our acceleration value in our calculation. Okay, that's pretty much it for this first topic, and then we'll move in the next topic on to gravitational potential. Thank you very much.